Welcome back. Okay, it's time to get serious about Coulomb's law. Last time, we discussed Coulomb's law as the expression that related the magnitude of the electric force to the product of the two charges divided by the distance between them squared and multiplied by a constant proportionality that we called K, where K, in SI units, turns out to be a pretty big number. We sometimes call it 1 over 4 pi epsilon naught, and it is approximately 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And we said that this expression is good to calculate the magnitude of the electric force, but I was always going to have to take care of the sign of the electric force by taking a look at the two charges involved. If I had two like charges, like two positive charges, they were going to repel each other. If I had two negative charges, they were also going to repel each other. But if I had two different charges, say a positive and a negative charge, they were going to attract each other. Okay, so it's time to do an example. So consider the situation where I have two charges, Q1 and Q2. Q1 is going to be the charge that I'm studying. Okay, so that's going to be the charge in question. And Q2 is some other charge that's going to be somewhere in the universe. And it's the thing that's going to be creating, so to speak, the force that we're going to be measuring on Q1. So I want to ask myself, what is the force on Q1? Okay, so we're going to take this in a couple of steps. First, in order to start any problem in electricity, I have to actually find out what are the charges involved. Right now I have a Q1 and a Q2, but are they positive, are they negative, what are their magnitudes? Let's say that Q1 is a positive charge, and I'm going to give it a sign E. So it's going to have magnitude equal to the fundamental charge, and it's going to be a positive charge. On the other hand, why don't we let Q2 be a negative charge, and why don't we make it minus E? Okay, so I have a positive E charge and I have a minus E charge. And again, I'm studying charge 1, so I want to know what is the force on charge number 1. Now, before I do anything, I always have to draw my coordinate system. For the sake of this example, I'm going to try to make work easy on myself in the long run and put my two charges so that one of them is aligned along the x-axis, the other one is aligned along the y-axis. And then I'll say that these two charges, the way I've defined my coordinate system, are about the same distance from the origin, and I'll call that distance L. So I know when I calculate the magnitude of the force on the free body diagram, I'm going to need some of these parameters in order to calculate what the magnitude of that electric force is. So, how many forces are acting on Q1? So far, I think just one. There might be a gravitational force, but we're not considering that today. And I think there's only one electrical force because there's only one other charge in the problem. So if I studied Q1 as a free body diagram, I would just put one force on it. Since these two charges are oppositely signed, I know that that force is going to be pointing from Q1 towards Q2, and so I'm going to represent it on my free body diagram by this line here. Then, and actually let me call it F12. And this is a notation that I'm going to use throughout the day today. And we want to think about F12, or the notation that I'm using here, to mean I'm looking at the force on charge 1 due to charge 2. Right? There are always two charges involved when I'm dealing with Coulomb's law. So the magnitude of F12 is given by Coulomb's law, which is K times the magnitude of Q1 times the magnitude of Q2 divided by the distance between them squared. And because of the way that I've arranged things, most of these numbers I know already, right? I know what K is. I know that Q1 is E. I know that Q2 is minus E. And now all I need to find out is, well, what is R squared? Well, if I look over on my picture, I can see that I have a little right triangle. And so I can calculate the distance here, R, just by using the Pythagorean theorem. And in fact, since I'm interested in r squared, I don't even have to do all of the Pythagorean theorem. I know that r squared is just going to be L squared plus L squared, which is just 2L squared. And so now I have the magnitude of F12. I can simplify this just a tiny bit, right? Because I can use my absolute value signs to get rid of the minus sign, and I'm left with something that looks like k e squared over 2L squared. But of course, the question that we asked was not, what is the magnitude of the force on Q1? The question was, what is the force on Q1? And so in order to complete this problem, I have to take the magnitude of this force and I have to turn it into a vector, right? The force is always going to be a vector. It needs a direction and an amplitude, or it needs me to fully define its components. In general, I'm more a favor of defining the components because I've already gone through all the work of defining a coordinate system, and therefore it's something that it's something that makes the problem very unambiguous if I define the x and y coordinates of the force that I'm studying. So to do that, I take my force and I'm going to redraw my coordinate system down here, and I know that my force points this way. And because of the geometry of the problem involved, I know that this angle here is 45 degrees. And so now I can calculate what is the x component of F12 and what is the y component of F12. And because I'm talking about components, I shouldn't have harpoons over my F12 because, of course, I'm just talking about the x component of F12 and the y component of F12. Now, I should say that whenever I do a problem like this, I always have to write SOHCAHTOA somewhere on my page, because SOHCAHTOA reminds me where are the sines and cosines and tangents of any angle that I'm looking at. Some people are afraid to write this down because maybe it's something they think we all know instinctively, or it's something that every good physicist should have memorized. But in reality, it's something that takes 2 seconds to write down in the corner of a page, and it's something that always helps us to make sure we get all of our trigonometric functions right. And so in between my two diagrams here, I'm just going to sneak in a SOHCAHTOA. And that's enough to remind me that the sine goes with the opposite over the adjacent, the cosine, the opposite over the hypotenuse, the cosine goes with the adjacent over the hypotenuse, and the tangent goes with the opposite over the adjacent. And so when I look at my diagram for F12, the x component is adjacent to the angle 45 degrees. And so I know that the x component here is going to be the magnitude of my vector, k e squared over 2L squared times cosine 45 degrees. And the y component is in the vertical direction, and therefore it's the angle opposite, therefore it's the component opposite the angle, and so I have a k e squared over 2L squared sine 45 degrees. And at this point you should say, but wait a second, these two things aren't completely right, because in my coordinate system I can see that my vector is pointing to the right, which means it should have a positive x component, but it's also pointing down, which means it should have a negative y component. And so this problem is not correct unless I've made sure that the y component that I've written down is actually a negative sign. And once I've done that, I've unambiguously answered the question of what is the force on Q1 due to Q2. But at this point you want to ask yourself, wait a second, what about all that math that you had me take? After all, you wouldn't be in this class if you haven't had at least 2 semesters of calculus. Is there a way for us to harness the mathematical formalism that you've been learning in your math classes so that I don't have to worry about all of the signs and taking care of the free body diagrams with the vectors on the... Is there a way for me to encode all of the information about the direction of Coulomb's law directly in my definition of Coulomb's law? And the answer is, of course, yes. So let's define Coulomb's law now in its vector form. So as you can see, I've written down F12, which again we read as the force on 1 due to 2, that is the force on Q1 due to Q2, and it's given by 1 over 4 pi epsilon naught Q1 Q2 over R12 squared times R12 hat. Now, before we get into what R12 is, because you can see that our definitions have changed a little bit, right? Instead of just having an R, I have an R12. Before I get into that, I want us to notice that somehow, by including this extra unit vector on the right-hand side, my charges, Q1 and Q2, no longer have absolute value signs along them. So by including the information about the direction of the vectors involved, and that's what that R12 hat really does, I'm actually able to use the signs of the charges as a mathematical tool to figure out in what direction does the force actually point. And so let me talk about two different vectors. First, I want to talk about the vector R12 as a vector, and this is going to be the vector that points to Q1 from Q2. And the second definition that I want to make is that the unit vector R12, which is by unit vector we mean that it has unit length, or that it has length equal to 1 in whatever system of units that I'm using. So it's a unit vector, but that encodes the direction from Q2 to Q1. So the vector R12 points from Q2 to Q1, but the unit vector just remembers the direction from Q2 to Q1. So let's take a look at this. Let's take a look at this somewhat more precisely. So imagine I have these two charges Q1 and Q2. I now define a nice coordinate system. How can I mathematically define the vector R12, which is going to point from Q2 to Q1? Well, in order to do that, I first have to define my two vectors R2, which is going to be the vector that points at 2, and I have to have my vector R1, which is my vector that points at Q1. Now, if I want to now develop a mathematical expression for the vector that connects these two, I know that it's going to be some vector sum of R1 and R2. And it takes a little bit of staring at, or perhaps a little bit of trial and error to make sure that you get the combination right. But I basically know that I want to start at Q2, go to the origin, and then go out to Q1. And so I want to go backwards along Q2 and forwards along Q1. In other words, this vector R12 is equal to R1 minus R2. Okay? And this looks like a difficult thing to mathematically represent, but when I start to do calculations with it, things actually start to get a little bit easier, because it's generically quite easy for me to write down what is R1 and what is R2, and therefore I can calculate R1 minus R2 rather quickly. And then if I want to convert this to a unit vector, all I have to do is say R hat 12 is the vector R12 divided by the magnitude of the vector R12. Right? If I take any vector and I want to make it unit length, all I have to do is divide it by its magnitude, and then I get a vector that's of unit length. So let's go back to the example that we just did. So I have my coordinate system, and I'm going to place one charge here, a distance L in the y direction. I'm going to place another charge here, a distance L in the x direction. I'm going to call this Q1, and I'm going to call this Q2. So let me see first if I can construct the quantities that I'm interested in. So R1 is going to point to Q1, and R2 is going to point to Q2. And so R1 is just the ordered pair, right, of the x component comma the y component. which is 0, comma, L. See, once I actually start doing the exercise, it doesn't seem as bad as when I was talking about it in more abstract terms. R2, on the other hand, is going to be at x coordinate L and y coordinate 0. Then I can just calculate. R12 is equal to R1 minus R2. Well, R1 is 0L, R2 is L0, and therefore R12 is L, comma, minus R2 minus L, comma, L. Right? How easy is this? The magnitude of R12 is just the magnitude of this vector, which is the square root of L squared plus L squared, which is the square root of 2 times L. And now I have all of the mathematical pieces that I need to construct Coulomb's law in its vector form. Right? F12 is equal to K Q1 Q2 over R12 squared, R12 hat. So this is K times Q1, remember from before, is equal to E, and Q2 is equal to minus E. So this is E times minus E, and I can't drop that minus sign here. Before, I had absolute values around Q2. Here, I don't have absolute values around Q2, and so I have to keep the information about, the minus sign with me. I then have to divide it by the magnitude of R12 squared, which is, I found it, right? So the magnitude of R12 is the square root of 2L, and so this is 2L squared. And then I have to multiply it by R12 hat, which is, of course, R12 divided by the magnitude of R12. Well, the magnitude of R12 gives me another square root of 2L. I'm going to actually plug in what I know here. So I have minus K E squared over, I have 2 root 2 L cubed. That's the combination of the 2L squared plus the magnitude of R12 times the vector minus L, L. And so this is, now let me distribute that common factor through, and I can cancel out one of the L's. I get the ordered pair that's equal to K E squared over the square root of 2L squared, comma, minus K E squared over the square root of 2L squared. Lo and behold, I've come up with an answer that I am perfectly happy with, right? So not only have I ended up with something that's a vector, but I actually didn't even have to take a cosine or a sine in here, right? And if I compare it now to the answer that I got, the answer that I got before, the only thing that's really different is the fact that here I have a cosine 45 and a sine 45. Well, the cosine and sines of 45 are going to give me a 1 over the square root of 2, and I'm left with exactly the same expression, and I even have the minus signs in the right place. And so this trick, although mathematically it looks very daunting, is something that's actually going to make my life easier if I'm able to keep track of all of the vectors involved. Now, in the next video, what we're going to do is we're going to take this description of Coulomb's law, which is great when I'm dealing with point charges, and I'm going to show how it's not only useful as a vector quantity, but it's also going to be useful to allow me to talk about forces due to charge distributions that aren't points. In other words, I could do multidimensional calculus with the very same expression.